So the title is a field scale comparison of 7 different soil sampling designs for nutrient recommendations. So on many Midwestern farms, especially corn and soybean farms that I'm familiar with, many of the growers have implemented some form of site-specific management or precision agriculture. And I use those terms sort of interchangeably. What I'm referring to is basically breaking a field down into smaller units and then applying some sort of management techniques to those units. So varying your treatments as you're going across a field. And this has been made possible by advances in GPS and GIS technology. Variable rate application equipment has become more available and less expensive. So it's been fairly quick to adopt, both in the commercial world and growers too. The cost of the technology too has made a difference in how many farmers can adopt it. Most of the tractors sold today have some sort of GPS capability. The desktop software has become much more easy to use. And as well as farmers have become more educated and more interested in technology like this. And the commercial suppliers, the input suppliers, especially the fertilizer suppliers, have all have the capability for variable rate applications. So more specifically for soil sampling, we still see a wide range of sampling designs in the Midwest. One of the things that I do on the farm is I do our own soil sampling. I also have about 15 other clients that I do soil sampling for, so mostly neighbors. Most of them are small. So I see everything from 2.5 acre grid sampling design all the way to whole field composite samples. And I would say maybe 10% of them are using grid sampling effectively. So we still see a large range of soil sampling designs out there. Traditionally, the recommendations have been to factor in soil type topography to direct your sampling to different blocks or zones rather than just the grid sampling. Although recently ISU has been recommending grid sampling. In the commercial industry, most of the input suppliers are gravitating towards this 2.5 acre grid sampling pattern and a VRT application for applying phosphorus, potassium, and pH. That's sort of the recommended size of the grid sampling that they're doing. And that's come down from as much as early as 5 years ago. A lot of them were in the 4.5 to 5 acre range. So it has been coming down already. So for my study, I had some specific questions. And the first one is this industry standard, or is this 2.5 acre grid size adequate for capturing the variability across a field? And if it is, or if it isn't, can we justify, or should we be using a denser sampling design to get a better idea of what the variability in a field is for directing our management activities? And could those be cost effective? And also, how much error do we generate in generating our fertilizer prescriptions if we use a less dense or a wider soil sampling design and then extrapolate that data over larger areas of the field? How much error does that introduce into our fertilizer prescriptions? So this is my study field. This is one field that my family's been farming for about 30 years. The reason I chose this field was it's the most uniform field that I could find, or that I had access to. There's very few soil types. You'll notice a difference along here. That's a Clyde-Floyd soil. And then around it is a cast and silt loam. The next slide will show that. But this field has had uniform management for the past 30 years. It has very little variation in topography and very few soil types, as we'll see. So here's a list of the soil types. The two that I talked about make up about 98% of the field area. And I don't know if you're familiar with these soil types. This Clyde-Floyd is also found in Iowa. It's more of a drainage way, sort of a darker, more poorly drained soil. And then the cast and silt loam is more of an upland soil. But in this field, there's actually an old tile line that runs up this draw. So actually, the wet part of this field is down here.
So there is a little bit of topography, with that being the lower area?
It's a lower area, but it's probably a matter of a few feet of a difference. It's a very flat field, especially for our area. That's right. The water will drain more out the northeast corner. This is Renard, the Renard farm. My family doesn't own this farm, but we've been renting it for a lot of years, as long as I can remember. So I sampled this field in 7 different methods, or in 7 different sampling patterns. 5 different grid sizes, the ½ acre, the 1 acre, 2½, 5, and 10 acres. And then also a block design where I separated the field into blocks and took composite samples within those blocks. For each sample, I sampled to a 6-inch depth. All of them had 10 to 12 cores per sample. On the grid samples, I sampled at the center point of the area. And my sampling covered an area of maybe 50 square feet, about the size of an ATV. In the block designs, I sampled randomly, sort of randomly. I drove transects through and stopped at random intervals. And I think I drove 3 transects through each block. So it covers a pretty good size of the area. So here's some maps where I'll show you the actual designs and where the actual points were taken. All of these were sampled independently. So when I laid out a design, they were all created and sampled independently of other designs. So I didn't use a dense design. I didn't pool any data to estimate larger sampling designs. The numbers that you see here are the sample IDs that I used when I had the testing done at Midwest Labs. And this was all sampled in the spring of 2010. Right before a bean crop was planted.
Did you put that in?
They're in the 150 to 200 range, almost all of them. So this is the 1 acre grid design. This one has 72 points. And the 2½, I think, has 32. And this one has 18. This is a 5 acre grid. I should mention this 5 acre grid is what we've typically been doing on our farm. That's when we first started doing grid sampling, which was around the 2002 area, about the year 2002. That was sort of the industry standard, was this 4.5 to 5 acre grid, depending on what you could fit in your field. And so this is the design that we've had in this field. Now it's been grid sampled for about twice now, and we've not yet used a variable rate application when we've fertilized. We just haven't seen enough variability, which you'll see later is we were probably missing it. So a 10 acre grid where I actually pulled just 8 samples from those points. And then here's a map of the block designs. And when I sampled these, I just drove a transect through here, stopped at random intervals, and I had, on my GPS, I could tell that I was within each block. And I think I did three transects through each set of blocks. And there's the 20 acre block design. I didn't bother with a whole field composite sample. That's something that on a field this size, we typically wouldn't do. Some smaller fields we might do, but a 72 acre field, commercially they probably wouldn't do it. Or they would recommend against it.
So what sort of blocking criteria did you use? I mean,
0, just a map. So there was no sort of agronomic criteria for blocking the fields. I just created.
So this is a 4-point grid.
Essentially, with a composite sample covering each of those block areas.
Oh.
So that's the difference between the blocks. The grid design.
Think back to that.
I don't have very good yield map data from this farm. I have 1 year of yield map data. So that really wasn't an option. The soil types, the way this other soil type lays, and I can go back to that slide. I thought it would be difficult to hit this zone, depending on how accurate the soil surveys are. I wasn't sure that I could confidently take samples within that block.
Well, we still could, I mean, it could be done by simulating that. I mean, just calculate the average of the density, but
If I could find an accurate georeferenced map of that, then I could pull out some of the samples that I took within that and do that analysis.
But even if we do that, you know, we have shown that those boundaries, you know, could be 100 to 100 feet off, or may not even be there. So that's one of the problems that we have with some.
And this is a pretty small distance.
Yeah.
This whole area is a quarter of a mile, so this may only be.
But, you know, you could actually see that visually from the aerial photograph. And they overlay each other to some extent. So you could have done it
You can see that roughly, but I don't know where it ends in here. You can see a little bit of a discoloration on this side too, and I don't know if that's the background, the aerial photograph, where it goes to a different paint. Okay, I think this might be where I left off. So once I had the soil data, I calculated the descriptive statistics. So the mean, the median, the standard deviation, the range, things like that. I also calculated the frequency of the results, and that would be in the interpretation categories. So the very low, low, medium, high, very high categories defined by the ISU interpretation categories. And frequency being the number of samples for that design in each category. So it's just a count in each category. And from the results, then I generated nutrient application prescriptions using ISU recommendations. I used the Ag Leader software, the SMS software. And then I looked at the cost of each design. And the cost included the sampling cost, the lab fees for processing the samples, any application fees for spreading fertilizer, and also the cost of the product. So here's some results. So these are the soil test phosphorus results. These are the interpretation classes that I used. You can see these three designs here, these three grid designs, generate some pretty complex maps. And this, I used a smoothing function within the software to take out the blocks. Right, and that was my point, is there has been livestock there, but not for 30 years. And this field hasn't had manure in 30 years, but yet we still see a high area close to the, and I see this in almost every field. And no matter how long it's been since it's had manure, it's Minnesota winter. You can't take a tractor to the end of the field all the time to haul manure in the winter. And we see this, it's a pretty common pattern that we see. And going back to my study questions, you know, one of the things I wanted to see is if this 2.5 acre grid is really adequate for estimating the variability in the field. So through these next few slides, I'll try to point that out. One interesting thing that I've seen through all of this is this 10 acre block design versus the 10 acre grid design. And through all the results that I'll show you, this block design really does a better job of estimating the field variability than the grid design, which you might expect. You know, you can't expect 8 soil, you know, specific points to really capture much of that field. And this, and I'll point out later too, this sampling design, if you factor in the cost of the sampling and the lab fees, is about $40 an acre. So it's very expensive. So if there was a better way to estimate that. Here are the potassium results. Some things in these results surprised me. This area of the field, all tested medium in the half acre grid, but this 1 acre grid shows a pretty large area of high. And I can't explain it, that's just soil sampling, I think.
See, that's that variability within shorter distances.
The scale of the variability is probably much smaller than what I ever sampled, is how I might say that. But look at some of these designs. This is, as I mentioned earlier, this is what we've been doing on our farm. And this is why we haven't generated any variable rate applications. It's why we've always just gone to a flat rate, fixed rate application, because we haven't been capturing the variability that's really there. One interesting thing that I've done is I've used this 20-acre block design and actually mapped a point where I took each core. So I would actually lay out maybe a 2.5-acre grid and only pull one core at each point and combine those into a 20-acre sample, combine 8 of those into a 20-acre sample. And that's allowed me to do it quick and cheap, which the farmers really like, and have some chance of being repeatable. So I haven't had a chance to go back and resample any of those yet, but so, which maybe it doesn't have any value when you pull data like that and your recommendations are extrapolated over such a large area, maybe it doesn't matter. But here are the pH results, and you can see a pretty typical pattern for a lot of Midwestern fields here too. This is a limestone gravel road up here. So you end up, when the dust blows across the field, you get lime applications that sort of are reduced as you go across the field. And some of the designs, approximate that pretty well, and even this one isn't terrible. For the pH, for looking at pH, the larger designs actually generate pretty similar recommendations to what the denser grids do, as far as amount of lime applied. This, I should mention, this is sort of a custom recommendation. This is what we use on our farm. This is what our local fertilizer supplier uses for lime. The recommendation here is 5 tons, 4, 3, 2, 1, and 0 for the spreading applications. So we like to have 6 categories there just so we can get that 5 ton per acre, which is really a high rate of lime for really fixing pH. So that's why there are 6 classes in here, and it doesn't exactly follow the ISU recommendations.
Well, we don't have classes.
Oh, don't. I guess I never looked. I planned on using this. Okay, so here's a lot of numbers. We have our soil nutrient categories here in each of the rows. What I really want to point out here is this column right here, this range column. You can see as the designs get less dense, we miss a lot of the highs and lows of what we're finding in our soil test results, and that's true for all of these categories. The range is really reduced. And sometimes it's drastically, there's a drastic difference there. But
another interesting thing that we didn't talk about is that it's a relatively well-behaved set, because you look at the mean and the median, there are some small differences.
Just going through there except for K.
Yeah.
K's got to skew.
Yeah, K we have, but normally it's much smaller than that. The difference with the mean and the median.
Mm-hmm.
See, with the mean, you may have some very high value or some very small, and then skew.
Mm-hmm. So what you mean is that these aren't accounted for just in a couple of really high samples. That there's more there than just 1 or 2 high samples.
Yeah, if you plot this, most likely you have a distribution that is not exactly normal.
Uh-huh.
It's like, I don't remember the name, but it has the
Not
right
normal?
tail.
Mm-hmm.
The right tail is longer.
Okay.
And potassium seems to suffer from that.
Yeah.
So it's because of the manure that you have. You have some sites that are really loaded,
Oh yeah.
and
Yeah.
so they're skewing the distribution to the high.
Mm-hmm.
So, and you can't skew them to the low end because you stop at 0.
Yeah.
So they go up to the right, but it's because of the cattle and the pigs or whatever it is.
Yeah. There were sheep at that, which is kind of unusual.
Wow.
It's not a typical farm for our area. They had a lot of sheep there at one point back in the early 70s, which I can remember as a little kid. I can remember the sheep being there, but now the pastures are all grown up. They haven't had livestock there in a long time.
Since you have a very uniform field, what type of range would you typically find if that field was not uniform? Would you expect to see?
That's a good question. Some of our fields, it depends on the field a little bit, because some of the ones that have been old dairy farms they can have incredible, we'll see phosphorus numbers, we'll see these maxes Well, the 130s are on the high end of what we would see. We won't see much over that. So I would say the normal ranges would not be too far outside of that on other fields. But especially the old dairy farms, these numbers would all be
Max that
higher.
they would really kick up.
Yeah,
Max value.
yeah, and the mean too. That they would be some of the farms that did a better job of spreading manure are more uniform or higher across the whole field.
Yeah, you can actually look at your variances there, it's a mean square standard deviation, and see how you design, template design relates to the major variability. So you definitely pick up more variation the smaller you print.
Mm-hmm.
Yeah, if you go to fields with a long history of manure, or it's much higher than that.
Mm-hmm.
Sometimes we go, I remember one field that had poultry manure. It goes from 2.5 ppm to 1,000.
Oh wow! I see very few over 100 on the phosphorus.
Yeah, yeah. The main problem is when you have manure.
Yeah. That's great. You guys got a lot out of that slide. I was hoping to just go over it pretty quick.
You're not buying time.
Yeah, I know. That makes me feel like I.
Well, when he showed me the presentation, I said, it's kind of long, so you have to go fast in some slides.
No, and I thought it was going to be fairly short. Here's some frequency distributions. I mentioned these earlier. These are the soil test categories. This one is for phosphorus. And you can see each design generates a curve or a line. And I was struggling a little bit with how to say this. The shape of these lines, the more similar they are, I would say that's a more similar representation of the variability in the field.
So what?
Yeah, I've been struggling with how to say this. If the shape of these lines is similar, then they're finding a similar proportion of samples in that category.
Okay.
And you can see the more dense designs, this being the 1 acre and the 2.5, have a relatively similar shape. And I would interpret that as saying they're finding similar proportions of samples within each category. And that maybe and if you have other ideas on that, I've been thinking about these for 6 months, and I don't have a great way of saying
Get
it.
rid of the lines and make it into a histogram. So
Okay. Mm-hmm. That's how I've seen it before. And the first time I saw this sort of representation was actually what we discussed at InfoAg. I saw one. That person was using these sort of representations and using bars for years from the same field. And as you could see the peaks move, you knew your management practices were either making a field more uniform, if your peaks got higher and more narrow. So I thought I would apply it here and look at the shapes of them. And you can see as your samples get reduced, your results really become more unpredictable and maybe don't capture some of that differences within the field.
And how, see, it's nice to see that this always happen, and that's because of the averaging of the data, how the proportion of the low in comparison with the rest goes down as the sample area increases. Doesn't happen too much with the very low, there are not many, but if you look at the low, see, in the grid samplings, the low is at least twice the frequency than the others. When you go to the plots, for example, it's about the same frequency. So the large area sampling hide some of the low spots.
Yeah, in this case it did.
And that's important for the prescription.
Right.
And the fertilization, the expected response.
That's a great point. Let me show for potassium. We see a similar effect on these two curves. Relatively similar for the 2.5 acre grid. And even the 5 acre grid is doing a relatively good job of capturing that one. And maybe even this 10 acre is. So showing similar shapes, but when you get down here, they just don't have enough samples to really increase the resolution of that.
Well, I think that's what it's a sampling effect.
Mm-hmm.
So,
This might even happen with random data. So is that what you're saying? It's
well, you're more likely to identify an outlier the more samples you take.
right. Mm-hmm. But you also create these peaks. So you'll catch more samples out here and here, but you'll also define these peaks. It's a little difficult comparing these types of curves because statistically, comparing sample sets with, or comparing distributions with much different sample sizes is difficult. So I mean, this is more of just an observational tool, which is the entire study. It's pretty much observational. But so that was for.
The first thing that we talked, I said, forget about that.
It says, yeah, it's not. Anyway,
It's pretty far above my ability. And then this was for pH, and you can see this 1 acre grid doesn't really approximate the half acre very well. This 2.5 acre grid does pretty well, but there's some discrepancy there. Okay, so going back to my questions, and this is really all the further we are. So you have to tell me if the time's getting to. Okay. So comparing the 2.5 acre grid pattern, if we go back and look at the ranges that it captured and how well it captured the variability in the frequency diagrams, it doesn't do too bad at estimating the variability, but it's still missing quite a bit. So now the question becomes, would a more dense sampling design or a denser sampling design better describe the soil test variability, and is it cost effective?
what's the answer to the first question? You think it's okay?
I think it's okay, but I think we can do a lot better. So I know that's not a very technical answer.
It's subjective in a way.
It is, and going back to some of the numbers, this was the number that I really, in these ranges, it does okay in the pH, but it seems to be missing quite a bit for the P and K.
Yeah, your standard deviation and your coefficient of variation is good for that. Yeah. Not as good, but a lot better than everything else.
Yeah. The question really becomes, is it cost effective to go to a more dense design or a denser design?
Okay.
Because I think a lot of times this 2.5 acre grid is really based on the time it takes to sample and the expense. I think is why the industry is really going that way. So from the results that I showed you, I generated some prescription maps, and these are the recommendations that I used. These are the Iowa State recommendations. This is for the first year of corn and a year of soybeans. So this is fertilizing for 2 years. So these are the actual recommendations that I used for 2 years. I put a 1 in the high testing category, and that was more for my own, for a check for myself, because that generates prescription maps that look exactly like my soil test result maps. So that helped me keep them organized to make sure I was working with the correct map at the correct time. So this doesn't really affect the application, but it allows me to maintain these discrete categories all through my maps. Here are the potash recommendations. Again, I put 1 in there rather than having 2 categories that are 0. Then they sort of get combined in the recommendation maps. And this is the lime application that I mentioned earlier. So here are the application maps I generated. They look exactly like the soil test maps, which was good for me to keep everything straight. So I can go through these pretty quick. That's the potash and the lime. So as I estimated the cost, these are the prices that I used. These were commercial prices that were quoted, that I called a co-op and got quotes for the prices for the products, for the dry application. These lab fees were from Midwest Labs. That's the actual fee that I paid.
What's the actual fee for non-stick?
It was over $8. So we had been paying, it was $8.80, and then there's a certain percentage off if you submit over the internet. So I think it ended up being around $8, but so I got them down to there, which was extremely helpful. So this is an example of the cost analysis, and I'm just going to show you the phosphorus one. The other ones look the same. I included, this was the total recommendation for the amount of fertilizer used in the field. This was the average per acre that the fertilizing prescription generated. So this was the cost of the product. The sampling cost was also a quote I got from a local co-op. The lab fees per acre. So on the half acre, it's twice. For the 1 acre with 1 sample per acre, it's $667. And also the VRT application. Now I used a VRT application down here when in reality, you know, someone may just go out and put some flags in the field. You may not actually use a VRT. You may not actually use the VRT equipment. So that gave me total dollars per acre on the phosphorus program. Yeah. One thing to notice is the amount of fertilizer that these generate. They generate a lot of dollars in fertilizer product, which makes them, you know, almost as expensive as doing a pretty dense grid sampling design. And that's going to depend on your field too.
Yeah. You know, the one thing your cost analysis doesn't take into account is the impact fertilization on crop yield.
Yeah, we've had this discussion too. That's a great point. If you could estimate the response of each of the crop, and you know, this might be money well spent, because you may generate enough of a yield increase even in the high testing areas, or even to make a difference. And all I'm looking at is the input side.
Right.
So that could be a future study, or someone could make a career probably of trying to estimate the yield responses.
We're going to work on this next week.
No. We're going to solve it next winter, huh?
Yeah, we were talking that I can give you some estimate of response
Uh-huh.
for the different classes. But he doesn't have nothing to do in the winter.
Yeah.
Right.
What do you think? Well, you can take care of the tree.
Oh, absolutely.
Okay, so any more questions on that?
No, just that this is great, you know, because again, it's a real thing. And yeah, that's the missing part, but that's okay. See, trying to add that component was going to complicate, but
Mhm.
and then of course the assumption, response, you know.
Mhm.
Oh, I wouldn't encourage you to do it. I'm just telling you
No, but
that,
it's important because
that $45 looks good to me until but I want to know that you have the same or more return than you would if you would have invested a little more in your sampling.
Yeah, no, that's correct. And this is where we've been on our farm. You know, we've been getting by inexpensively, but I think we've been missing a lot of variability in the fields with that sampling design. If I were presenting this to a farmer, which I probably will, you know, that we don't take the time to estimate our yield response from our management, from our fertilizer applications. It's something that we don't do on the farm. So maybe they wouldn't even understand. This is more of a, we measure yields, but we don't necessarily go back and line it up to the fertilizer applications.
Wow.
Maybe we should be, but.
You're just trusting people.
Well, for one thing, we're not sure it actually got applied that way, I guess, but.
So you don't trust your variable rate equipment, you don't trust your yield monitor.
That's a good question. The yield monitors are typically off by a certain percentage. if we look at across our entire farms. But we do trust them, we do use them. Typically,
You trust Antonio more than you do your own equipment, is what I'm saying.
yeah, we kind of put fertilizer on and then we get a yield, but we don't really go back and try, for one thing, we're fertilizing for 2 years. And then, so you go back and try to put 2 years worth of yield maps together and say this area got this rate of fertilizer and was a high yielding area or a low yielding area. That's something we just haven't done, which is a lot of data to dig through.
Even if you do that, it's not good.
Because of the interaction with climate or weather?
Yeah, you cannot correlate absolute yield with soil test. You can have some estimated response.
Mm-hmm.
Yeah,
The
but
only way of really doing that is putting some strips in the field. So
Okay.
you put some strips and then you have application, no application,
Mm-hmm.
and then you can compare.
Mm-hmm.
I would suggest that if you trust Antonio more than you trust his equipment, you buy new equipment. Sorry.
all right, well, we'll argue.
Does that answer your question,
That's a
or?
good point, and actually for you, given the knowledge you have and the equipment, I really encourage you to do that.
Mm-hmm.
You can very easily have 2, 3 no fertilizer strips
Mm-hmm.
across the field, and then you can check. Now, don't trust what you get 1 year in one field.
Right.
You have to do that several fields and
Mm-hmm.
2, 3 years, because that will give you a really good idea of where you are.
Mm-hmm. That's a good point.
So basically, from this table, we're doing 5-acre grids.
Mm-hmm.
That value is almost half of what you would apply in the 2.5. So you'd actually have to increase the amount you're putting on there. So that would potentially affect your output. Is that what?
Yeah, theoretically, yeah.
You're saying that you're not putting enough on a 5-acre grid?
Because we're probably missing some of the low testing areas, and that's why you can see the application that it generated was.
But you're not missing with the 10-acre grid.
Well, no, this seed, you don't know.
Well, you don't, but look at the difference in, you get 162 on one with 2.5 acres, 142 with 10 acres, and 96 with 5.
See,
Well, now this is where if you'd have taken just samples
Yeah, this doesn't
and
tell
not,
you
or not independent.
what
it
the
might be
results.
something different, yeah.
I mean, everything, and then it changes a lot from field to field.
You need to put
Mhm.
those prices in bushels of crop, and then they don't seem so.
Yeah, but the
dramatic.
key, Sean, the key is that, see, depending on the proportion of any lows or low, see, and those $93, well, forget about half acre, I don't think it's good, but the 1 or 2 acre,
It's the
if
difference
those
between those
lows
two.
are really
It's the
true,
differential cost, it's not the.
then that would generate a response that they would pay for that.
It was profit
And then at the
margin.
same time, he wouldn't be applying
So what's
some high.
$22 in terms of corn prices at the moment? 3 or 4 bushels?
Yeah, 3.
So, yeah, depends on whether you get a 3 or 4 bushel pump for having same
That's
technology.
tough to measure.
Yeah.
I think you get it, but
Well, the real question for me becomes, these designs, you're generating a lot of fertilizer application. So what's the value of fertilizer placement? Do you feel like, and try to explain this to me, a farmer, do you feel like this was efficient use of your fertilizer dollars? Some of this is most likely going on in an area that's not likely to respond.
exactly. Yeah.
And so do we feel like this is a more precise application where every pound of fertilizer on there has a greater payback since it's going on an area of the field that's more likely to respond? And that's a tough thing that's a
Yeah.
difficult question.
Well, one thing we need to talk about at some point is that you're talking about one field.
Right.
And all of your recommendations and your interpretation really relates to one field. And
Right.
It's difficult to extrapolate it to all fields
Right.
in the universe. And the more variation there is in a field, it seems to me the more likely that intensity sampling will pay.
Right. And that's why I picked a field that I thought was uniform. If you pick a field that you feel is already highly variable and you show that a more dense sample is the most cost effective. That maybe isn't as interesting as if you say, this is one field that we wouldn't expect to have to sample at a high density, but it paid anyway. And that was sort of the intention behind picking a field that I thought was as uniform as I could find. So.
See, the other reason that things get complicated is because this is really complicated. Because we did this in about 70, 80 fields. So we actually tried to have a uniform rate and a variable rate. You've seen some of
Mm-hmm.
that. So what is happening is that what I am discovering is that actually our recommendations do not really apply well for variable rate and then some.
Okay.
So we should change the philosophy of recommendations, because if you are actually going to then something and RT, then you should take some of the insurance, that normally we have in the recommendation. You see?
Uh-huh.
And then that
Yep.
will change the rates applied for the very low and the low.
Mm-hmm.
See? And that's why you read some of those papers that we
Yeah.
published. There is no effect on yield.
That's why you don't often see a yield increase.
Fixed and variable rate.
Yep.
And that's because of the rate we are applying.
Right.
And it also depends, of course, in the proportion of the lows versus the high.
Mm-hmm.
If you are in an area that you have, say, 10% of lows or less, or you have 70%,
Mm-hmm.
then that also changes how you
Yeah.
approach things. So it's really complicated.
Mm-hmm.
Have you written that up? Have you
Yeah.
talked about that also?
Oh, yeah.
Yeah, that's really good.
So the real advantage is,
Fundamental change in the way you think about developing fertilizer.
Exactly, because we are using recommendations based on a 40-year-old concept
Mhm.
of something that is a new technology and a new philosophy.
and the real benefit of that technology comes
Yeah.
right in something like this, where you're applying less fertilizer.
But it's so, that's one of the things that I learned about going to Argentina, because see, down there, it is the other way that we have here. See, there, most of the fields are low, and the small area is high.
Mm-hmm.
Here is the other way around. So how you approach this is completely different.
Yeah.
And then in terms of what is the risk of making a wrong recommendation, depending how things are for different fields in your farm, changes that too.
Right.
Yeah.
So, but I think this is great as from an education perspective, of course, with the clarification that we don't have the response.
Mhm.
So that may affect that.
This is easy for a farmer to understand just from the input cost side, because that's something we pay extremely close attention to.
But I encourage
And-
you to have some strips. And then if you
That's a
don't
good
have
idea.
figures, then come to me.
Okay?
And then I bet that you will say, what the heck I learned? I'm measuring because of the thing I learned. That would be what you would find.
Uh-huh.
Okay.
Okay, so I use the same process for both the potash and the lime recommendations. So this is a total cost analysis of this fertilizer program. It includes the cost of the monoammonium phosphate, the potash, and the lime, the sampling cost we've seen before, the lab fees. So this all was just used once with these three products. So these are the results. And we see this. These are not terribly different as far as the input cost side. These two seem to be quite a bit less expensive, but I would question whether it's catching enough of the variation of the field. And these tend to be more expensive just by the amount of fertilizer that they generate.
The other important thing about lime is that the costs vary a lot depending where you are.
Mm-hmm.
If you are in an area that lime is cheap.
Mm-hmm.
If you go to Northwest Iowa, that's 5 times more expensive.
Mm-hmm.
See? And that's the main advantage of grid sampling and variable rate now in Iowa. is for lime.
Yeah, and we've used it most for that. It could save a lot of money. From my experience on our farm, it cuts the cost of our applications in half.
Oh, yeah.
We use about half the lime that we used to, as opposed to just putting a 4-ton rate across the entire field. Our average rates now are more like 2 to 2.2, 2.4. So we've seen a lot of,
And how often do you apply?
probably once in maybe 7 or 8 years. So it's not we don't have to apply it very often. But it really helps to have the grid sampling and find those really low areas and really hit them hard. So here are the components of each of the expenses by design. You can see this right here, the lab fees and the sampling cost is about $40 per acre. And then it gets cut in half about every step. So this one is around 20 and this one is around 10. VRT application is the same across all of them. And then the cost of the fertilizer products are the bottom three layers on these bars. So I ran these same numbers then with a low, medium, and high fertilizer price scenario. My question was, as fertilizer becomes more expensive, should we be spending more money on sampling and trying to use less product and try to make better use of those dollars? And you can see in a high scenario, you can see that these designs become very expensive. And actually the difference here becomes magnified as well. And I can show you the numbers. So these are the numbers that I used. This medium scenario is approximately where we are now. And these numbers, we've seen these get extremely high, like in 2008, those were over $1,000. And as early as 2002, these were more like $200. So we've seen wide swings in the cost of fertilizer. And going forward, we're probably headed more towards a high scenario. Okay, so
in West Iowa, the line is $32.
that's a huge expense for those farmers. They don't have to walk fields endlessly for aphids either, though. That's what we've been doing for the last 2 weeks, is walking for soybean aphids. So the second question is, can these more dense sampling designs be cost effective? And my argument is that they can, when we look at a total cost here. That shows me that just from the input side that there could be an incentive for going to a more dense design, to a denser design.
How do you see that compared to the 5 acres?
You know, that's a good question. This looks inexpensive, but just from looking at the application maps that they generate, it's missing low areas. And that's just my observation. So in my opinion, these are better fertilizer applications than these.
So what's that opinion based on?
Just the range of soil tests that's captured, the variability that's captured in the field.
But you're making the next step. You're assuming that managing that variability is going to lead to more production, right? More efficient production.
In these designs or these? In the denser grid designs, we're placing the fertilizer where it has a higher likelihood of generating a response. And these, by missing some variability, these are not as good applications.
You have to make that assumption in order to draw the conclusion that you draw.
Right.
That assumption's wrong.
That's a good question. I know you did. I don't have a good answer for that. Just what the deciding factor in my mind was some of the looking at the nutrient maps and seeing how it's, you're extrapolating that data over a larger area. And in my mind, that's not as good a fertilizer application.
Yeah, I have the same sort of faith you have in the technology, but it doesn't prove it.
Right.
It's just it's an opinion, right?
Mm-hmm.
The thing is that, but this is an important issue because, and that's what I'm actually talking out there mostly about these issues, is trying to move away from large areas to sampling. Because there is something that, of course, Pat didn't say, but the cost of soil sampling and testing, if you compare that with the cost of fertilizer, it's half or 1/3 of the cost it used to be 10 years ago.
Yeah.
Oh, plus
And then people are spending all this
Mhm.
money in these other things, much of that they shouldn't be spending. This expensive seed, all this stuff. And then, for not spending, a few dollars more per acre in fertilizer, fertility, they're just guessing, you know.
Mhm.
So that's the issue. Now, yes,
Mhm.
I have some data that could kind of prove what Pat is assuming. Of course, we don't have it in this study.
Mhm.
And some of the soil survey guys here and other universities sometimes get angry about some things I say when I tell them for PMK, soil map is absolutely useless. So,
Mhm.
see, and, but I have the numbers that prove it. Because see, the theory is the soil type because of the genetics, you know, the total nutrient availability, the availability of the nutrient and the impact of yield and removal should be related to nutrient levels. But that's if you don't have fertilization during 100 years. Essentially change all the patterns of variability in the field. So now when we look at the impact of soil type or even topography and yield, it's not there or it's inconsistent. I mean, you go to the Des Moines low, and you have the low areas in a dry year have the highest yield and the higher removal. You go to a wet year and you have the opposite.
Mhm. And we would see that in this field too.
Yeah, and that's why you see this. I mean, it doesn't make sense that people keep doing this.
Mhm.
And in that publication, you know, with Sawyer, we were kind of mild, you know, because it still is recommended, you know, but really it doesn't make sense.
Mhm.
I wouldn't go so far to say, yeah, go ahead with.
And
with
farmers
1
don't
acre.
really have good soil classification information, right?
But
They don't have very accurate soil
No,
classification.
but we
Or
did. I mean, I had Tom Fenton working for days, you know.
Mhm.
No, I
in a
think you
field,
can
and we
do
have
it.
the detail, yeah, but even with the detailed maps, it doesn't work either.
Okay, so, but,
Yeah.
yeah, so what you're saying, it makes a lot of sense to me.
Yeah, so.
No, I agree. We don't have we can find it. You know, I can go on Web Soil Survey and I can outline my area and I can get a map that looks reasonable to me as far as the soil colors and things like that. But most
But
most
in
farmers
Iowa,
have a book.
See, in Iowa, we have some of the best digitized soil survey.
Mhm.
It's just 12,000.
Mhm.
I have no idea in Minnesota. But you go, you go to some other states, and they're using 120,000, 50,000.
Mhm.
So it's even worse.
Yeah, I think Minnesota is in the 1 to 20.
Yeah,
I think it's maybe twice what yours.
Remember exactly.
So I'll try to, this next section, I'll try to get at your question. So how much error are we actually generating by extrapolating this data over larger areas? And that maybe get, you know, will help answer your question or generate some discussion on your point anyway. So in these numbers are the amount of field area, the number of acres in each of these classes. And this one is for phosphorus. And this is the half-acre grid I used as a standard or as the correct value. For each of these designs then, I calculated the number of acres that they found in that category, the difference or the discrepancy from the half-acre grid and what percentage of change that was. And once I had these numbers in red are what I define as, maybe unacceptable error or an inaccurate application, or would generate an inaccurate application as being greater than an error of 50% of the field area. So as we can see, as some of these designs become less dense, we see some pretty high discrepancies with the amount of field area that this one found. And these error numbers become pretty large. And a design like a 1-acre grid, while there's still error in all of the categories, we don't see the large errors like we do in some of the other designs. So hopefully that, is some evidence that maybe these designs like the 10-acre grid that might look good probably aren't generating a very accurate recommendation.
Yeah, we're not a tough audience to sell.
This is something that that I found interesting as I was doing it. There's a pretty large error here, but when you look at some of these other numbers, especially that one, And that's finding, that's generating an over application by finding a lot more area in the low category.
You know, if you want to move population, I mean, you could really strengthen it by using all of the points as your standard reference map versus the point.
That's a good idea. And then I have
Otherwise,
this.
it's fine the way it is. There's nothing wrong with it.
There's no improvement needed. So here's for potassium, again, using this as the standard, and again, these are the number of acres in the field in each of these classes. And we see some pretty large errors where it's maybe a little hard to interpret it. Here, 3 out of 4 are pretty far off.
Potassium is always more variable.
So this gives me some confidence that maybe this design is detecting, is representing the field at least as good as this, or at least more similar to that design. So I don't know if that gets to your point a little bit of how do we know if that's generating a good recommendation, or are we using our fertilizer more effectively? And then this is the same representation for pH. Again, you can see some of these designs are generating some pretty large errors when we compare them to the half-acre grid. Okay, so we're getting towards the end. So in conclusion, the 1 acre grid pattern was slightly less expensive in total than the 2.5 acre grid. And it captured more field variability as shown by the range of values. So my assessment is that we can justify going to a 1 acre grid over a 2.5 acre grid, even in this field where we would expect a lot of uniformity in the soil test values. And these designs also reduced our total fertilizer usage. The large block patterns resulted in over applications, and in many cases were more expensive. The dense grids generated fewer application errors, which we showed by they estimated either too much or too little of the field area in each interpretation class. And this gets to your point that if we really wanted to do a cost-benefit assessment, we should include more benefits in terms of yield. And that would be a good thing to look at.
So I have a question, just a general question. Would you come to the same conclusion had you done this experiment in a different field?
Most likely, I think I would have. But my opinion is I think I would have if a field had more variability than this one.
So we went to southern Iowa, and
I don't know.
exponentially more variability than what you have.
I believe I would come to the same conclusion.
The half acre wouldn't do better?
Oh, I think it would. This is something I should have mentioned. That it's just too expensive. And that's why I'm recommending more instead of going from the 2.5 acre grid to go more to a 1 acre grid. But the half acre grid is sort of beyond the scope of what most farmers would do.
Yeah, but your part of your rationale is the savings in fertilizer, right?
Right.
Right. So you wouldn't save more if you were in a different field.
Oh, a half acre grid could be the best design in a different field.
That's what I'm asking.
Yeah. No, I agree. It would depend on the field. This.
That's exactly my point.
Yeah.
Yeah. So, but it's fine.
This is useful for me because I farm this field, and that was sort of the this has a lot of value to me.
Yes.
So.
and it's a great learning exercise.
Right, and the same process could be applied in different areas of the country. I think the same sort of analysis, but you may not have the same conclusions.
Fields like that where you repeated this experiment. It's definitely good for you.
It's great. It's great for me to have this on paper and pull the samples and see it and be able to talk to my clients that I sample for and show them, that in our area, some of the sampling designs that they ask me to do are probably inadequate.
Yeah, I think that's all fair. Yeah.
So that's what I'm taking away from this. That's how it's more useful for me. So, but it's pretty light on statistics. It's pretty hard to prove a lot of the things that I see in the data.
What do you think the source of variability is in that field that was supposed to be very uniform?
That's a great question. Our yield maps still come out variable. The one that I have still shows a lot of variation. And I don't know if it's hydrology or if it's, some of the really small scale agronomic things like stand. If you have an area that's maybe an acre where you have a half a stand for some reason, if you get a high clay soil type and you get a hard rain and you get a reduced stand, and maybe those effects can last for a long time. That's a great question, though.
How many? That's been farmed what? 60 years? 70 years?
I'm sure all of that.
Pounds of P and K added annually.
Our recommendations are mostly like 250 to 300 pounds of potash for a 2-year cycle, and our phosphorus is more like 100 pounds of MAP for a 2-year cycle, plus some starter fertilizer and things like that.
See, we've had those applied for decades,
Mm-hmm.
and when we do something like this, we're assuming everything's been applied uniformly.
Right.
Manure has been applied somewhat
Mhm.
reasonably uniformly.
And this field hasn't even had manure in 30 years, probably.
Right. See, I'm just wondering is when you look at that field and the soils map and it looks uniform, well, maybe if you would have taken a soil sample of that field before we started messing with it, in terms of applications, it would have been more uniform than it is today.
That's a good point.
Test time.
I don't think,
Oh, yeah.
you think so?
That it could come all the way back from the native vegetation, even, because
That we've introduced variability?
Yeah.
Only in the sense of the livestock. I mean, you're applying a uniform.
You're assuming it's more uniform.
Well, but you see, is the non-uniform application and the residual effect of P and K. Those are the two things. Nitrogen, you apply nitrogen today, next year is nothing there.
Mhm.
But the P and K will stay forever. And actually, we see that. Actually, my first work in Uruguay, the soil sampling, was in 1971. We sampled fields that never had been fertilized. Those that have been fertilized with broadcast, and those that have been fertilized with ban application for 50 years.
Mhm.
Oh, it was amazing. Those that have not been fertilized, the variability, I mean, you could take one sample in the entire field.
Mhm.
See, but the others, so it is by far the application. The other thing, there's a group of farmers that work in Argentina, that they're working in an area that P was high always. So they have been cropping alfalfa crops for almost 100 years. They started applying for fertilizer just about 5-10 years ago. And you have variability now that goes between, say, 15, 20, 30 parts per million. But it's not much variation.
Mhm.
But then you go to another field that originally was, say, 2-5 ppm, and now it's in that range. 20 to 30 parts per million.
Mhm.
The variability is something that you're showing.
Mhm.
So it is the application of that.
But
Now,
you you also have a differential amount that you're removing if your yield variability is
Right.
as great as what you're saying.
Right.
Exactly,
Application
but the science is
and
very good because we can measure that, the impact of that in large areas, and that is the case. But what we don't know yet is the impact of yield variability in the small scale.
Mhm.
But you've
That's
only
correct.
measured 3 variables. So,
Right. This is all just pK and pH.
yeah, and so collectively, do they account for what percentage of your yield response?
Oh, that's a great question. I'm not sure I can answer that. I'm sure I probably learned that 5 years ago in a class.
Well, it depends
But-
probably. But there are other soil characteristics that have some leverage on yield.
Mhm.
Good measure.
Mhm. Hydrology, I think, would be an important one in this field.
Seems to be soil physical properties
Right.
that control yield in Iowa on a larger scale
Mhm.
than
But with only 2 soil types, the physical properties shouldn't have wide variation with the not having as many soil types, assuming that that soil type is uniform in physical properties, which maybe it isn't.
Yeah, by far the main source of variability in yields cornerstone in Iowa is physical properties in terms of water availability, excess, or defect. That's something that farmers are mistaken over there. I mean, they believe it is the fertility or the weeds or the insects. It's not. It's just soil and rooting, all the things that affect.
Does that make management zones more difficult to establish?
Yes.
As far as some management zones might be your high yielding in 1 year, but if it doesn't rain, it may be.
But if you know that, that's useful information.
Yeah,
But can you plan ahead?
It depends on how, when it's.
Yeah, no, go ahead.
Right.
No, it doesn't matter. Yeah, I mean, if you look at that paper by Sochi, I mean, you will see that the relationship between absolute yield and the management zones that we established is very good.
For what you measured, probably not, but for nitrogen, potentially.
I don't know.
Okay, well, you're not correct, but it could potentially delay your nitrogen application.
That's the word, potential.
How much yield variability was there in your map?
This field, the average is about 190, and it's hard to tell because your yield maps, the low end is where you're opening up fields, or your combine doesn't measure that quite as accurately. The high end was up in the 215 range. So if we assume maybe we have the same variability throughout the field on the low side of the average as we do on, it probably is something like 175 to 215.
That's not very bad, but that's pretty good.
Yeah, it's not highly variable, but on the small scale it can be. So.
This is why we didn't mess with nitrogen. The nitrogen is more complicated. Yeah. And the concept of variable rate for nitrogen, there's lots of discussions. But Ken is right in the sense that knowing what happened, it could be potentially useful.
Right.
Now, what happened out there, for example, that we are seeing is that it's the contrary of what farmers believe. See, what most farmers are doing is apply more nitrogen in the high yielding areas.
Right.
Unless in the low yielding areas. Well, it should be the other way around.
Okay.
Because in terms of the proportion of response, actually we need more nitrogen in the low yielding areas than the high yielding.
That's your money is better spent there.
Because of the
crop response.
Between total nitrogen uptake or removal and what is needed. People confound those two issues. And they come up with the wrong application.
Okay. No, those are great questions.
Yeah, but going back to the issue of the variability, yeah, it is mainly, well, of course, some exception. For example, you go in soybean and you have SCN or not SCN, but even SCN is related to soil, soil properties, and pH and moisture and organic matter. So, normally the physical properties, in terms of yield,
Okay. I think that's all I have. I'd like to say some thank yous. First, Dr. Malorino, he spent a lot of time on this. He's taken a farmer's presentation and turned it into something that looks and sounds scientific. Thank you to Dr. Cruz and Dr. Moore for putting the time in today. Also, the Virgil K. Webster Scholarship Committee. They were very generous with me, and they without that help, I may not have made it through. So that's been a great help to me. Jeff Newman at Farm Country Co-op. We've had numerous discussions on the golf course of fertilizer sampling techniques. He's the manager of the agronomy department at Farm Country Co-op. That's in Pine Island of Minnesota, and he gave me the price quotes on the sampling designs and fertilizer costs and things like that. Also, I mentioned John Mengidi, who gave me a break on the soil sampling fees. Jesse, Dawn, Jackie, who I've been pronouncing that JC. Also, Tom, thank you for all the help you've given us all the way through the program. So without those three and Tom, maybe I also wouldn't be here as well. So thank you.